Alright, we move into a more interesting topic called the pumping lemma. The pumping lemma allows us to answer the question, is A regular? Where A is some language. The pumping lemma we deal with here is the pumping lemma specifically for the regular languages. The pumping lemma exists for other languages as well, such as context-free languages, but we will not be dealing with those here. So one must understand the following point, that the pumping lemma only allows us to prove that a language is not regular. It does not allow us to prove that a language is regular. What I mean by this is the following. The pumping lemma states that if a language is regular, some conditions must hold. Right? This is assuming that a language is regular. However, the pumping lemma does not say that if conditions mentioned hold, then the language is regular. So this relation is not stated by the pumping lemma. Alright. So the pumping lemma, I'll repeat, only allows us to prove that the language is not regular. Let's move on to the statement of the pumping lemma. What does the pumping lemma say? The pumping lemma says that if the language A is regular, then there exists some pumping length P. Okay, there exists some mysterious pumping length P such that, and we don't know what the pumping length P is. Okay, we don't know what this number is. It's some length. This pumping length exists such that for any S, where S is a string in the language A, and the length of S is at least P, alright. So if S is a particular word in the language A of length at least P, then the following conditions must hold. For all positive integers I and a breakup x, y, z of S, x, y raised to I, z must belong to A. Y raised to I here indicates y repeated I times. I must be either 0 or more. The length of y must be positive. By positive meaning not including 0, right? So it has to be 1 or more. And the length of x and y taken together should be less than equal to p. So given a language A, if the language is regular, there exists some pumping length p such that for all strings s in the language of length at least p, and for all ways of breaking it up into 3 parts x, y and z, we have x, y raised to I, z must be also in the language A, where I is a positive integer. Length of the middle portion must be at least 1, and the length of the first 2 parts x and y together must be less than equal to the number p, although we do not know the number p. Right? So let's look at an example of how we use the pumping lemma. So consider the following. Is the language B containing strings 0 raised to n, 1 raised to n, where n is more than equal to 0, is this regular? Is this particular language regular? So we do not know, so we assume that yes, let this language be regular. So if the language is regular, by the pumping lemma, there is some number p called the pumping length, and for all strings s of length at least p, right, we can pump it by dividing into 3 parts. So to disprove that the language is regular, all we need to do is find a single string s such that, and a single string s such that there is no way of breaking it up wherein it can be pumped. What does this mean? So let's consider a string s which is 0 raised to p, 1 raised to p. Alright, so this is a string. This string satisfies the fact that the length of the string is at least p. Now we need to look at all possible ways of breaking up S. So what are the ways in which we can break S up into three parts? Okay, so we need to break this up into three parts, X, Y, and Z, such that length of S is at least 0 and the length of XY is at least uh, is more than is less than P. Alright, so quite obviously, since X and Y to be taken together have to have a length less than equal to P, and the string is 0 raised to P, 1 raised to P, X and Y being in the beginning of the string, X and Y will always contain at most only zeros, right? X and Y will never have any ones, because if we look at the string, by the time we get to ones, we have already taken up all p zeros, and since X and Y has to have a length of p or less, uh, we will have exhausted uh, all units of length of X and Y before we reach the ones. Okay, so let's proceed. So that means we now have a narrowed down search, so to say. Now how do we break X and Y further? So X and Y will definitely contain, this contains only zeros. Okay, and Y has to be of length at least 1. So Y will contain at least one zero. Now X and Y can be anything less than P as well. So X and Y can be P minus 1, P minus 2, P minus 3, anything. So there are essentially two ways we can do this. So let us assume that X and Y take up exactly all the zeros. Okay, that means Z contains 1 raised to P. If Z contains 1 raised to P and X and Y take up all the zeros, with Y taking up at least one zero, what will happen when we pump Y? Okay, when we pump Y, we will get, with X equal to 0 raised to I, sorry, let's call it 0 raised to L, okay, let Y be 0 raised to M, such that L plus M is equal to P, alright, and Z is equal to 1 raised to P. Now in this case, when we pump, what happens is we get X raised to L y raised to, sorry, we get X followed by Y raised to I followed by Z, and this turns out to be 0 raised to L followed by 0 raised to M into I, because 0 raised to M is repeated I times, followed by 1 raised to P. Now only in the case where I is 1 is L plus M into 1 equal to P, right? For any other value of I, L plus M into I is not equal to P, right? Therefore the length of the number of zeros that are there in the string and the number of ones will not be equal. Let us consider the case wherein L plus M is less than P, wherein M is also greater than 0. When L plus M is less than P, a similar thing will happen. Z will contain zeros from P minus L minus M followed by 1 raised to P, right? Why? Because L zeros are in X, M zeros are in Y. In this case as well, for I other than 1, what we will get is a string 0 raised to L, M raised to 0 raised to m into I, 0 raised to p minus L minus m, 1 raised to p. And this will turn out to be L plus m into I plus p minus L minus m, which is equal to p plus m I minus 1, right? And only when I is equal to 1, this is this factor 0, equating this to p, and is not equal to p for all other values of I, right? So in no way can we break up the string and pump it such that the word will belong to the language. Therefore, our assumption that B was regular is wrong, and therefore B is not regular.